Hello and welcome. In this module we will continue and wrap up our discussion on dispersion, and then we will also talk about attenuation very briefly, and that would be the end of our fiber parameters as far as this particular course is concerned. A few of the remaining fiber parameters like nonlinear effects will be considered as and when they are required in the later half of the course. You might have studied in the earlier module about dispersion, and we have talked about it. Dispersion is a very general name for the dependence of the propagation constant beta inside a fiber with respect to omega. If this was a linear relationship, as in for the case of a free space where we know that beta is given by omega into square root of mu epsilon, and assuming that mu and epsilon are constants, right, with respect to frequency, then beta will be a linear function of omega, and we have seen that the derivative of beta with respect to omega is basically the inverse of the group velocity. So, this group velocity will be equal to a constant because del beta by del omega will actually be a constant, and we have also seen that this del beta by del omega evaluated at the carrier frequency omega 0 is denoted in a shorthand by writing this as beta 1. We have also seen that you can expand beta of omega around the carrier. So, you would actually get the first term omega 0 plus we know delta omega into beta 1, where delta omega is the deviation of the frequency from the carrier frequency omega 0. We can also expand this to the second order. So, getting delta omega square of 2 multiplied by beta 2, where beta 2 corresponds to the second derivative of the propagation constant with respect to the frequency evaluated at again at omega equal to omega 0. Of course, in writing these equations we are assuming that this spectral width delta omega is very small compared to the carrier frequency omega 0 itself. Okay. So, as long as this is true, you can expand beta of omega, and you will see that the presence of non-zero values of beta 1, beta 2 is the reason why you get dispersion. Okay. Beta 1 tells you how the envelope gets delayed, while beta 2 tells you how the envelope actually gets spread. For that reason, this beta 2 is called as the group delay dispersion term or the group velocity dispersion. Okay. Because beta is inversely proportional to beta 1 is inversely proportional to 1 by Vg. If you consider a length of L, then L by Vg will correspond to the group delay. Okay. So, this term beta 2 can then be thought of as the variation of group delay with respect to frequency, and therefore, this can be considered as group delay dispersion. How does tau g vary as a function of omega, as well as because 1 by tau g is corresponding to Vg, the group velocity, you can call this as group velocity dispersion parameter as well. Okay. So, it is sometimes not specified which one you are talking about, but the context should make you clear. This is typically called as GVD parameter. Okay. Although strictly speaking beta 2 should be called as group delay dispersion, and 1 by beta 2 should be called as the group velocity dispersion. Okay. Anyway, the point to note here is that dispersion, whether it is material dispersion or the waveguide dispersion, which we talked about in the earlier modules, can be encapsulated into this formalism where beta is a function of frequency. Okay. We have also seen what happens to a input Gaussian pulse of certain width T0. What happens to this pulse as it propagates through the fiber, of certain length where beta 2 is non-zero, is that the amplitude decays and the width also increases. In addition to that, there will also be a chirping, right. The carrier frequency will start to increase or decrease depending on whether the GVD parameter is positive or negative. Okay. So, this positive or negative chirping would happen, and we have seen a certain expression for obtaining this pulse width as a function of beta 2. Now, let us get back to the dispersion in terms of material dispersion, wrap up that discussion. We have looked at the group velocity ng, which we had defined, right. Now, we will actually look at the reasons why you get ng. Okay. So, material dispersion is actually the property of the material itself. Okay. So, material dispersion is a property of the material itself. So, we have discussed ng, the group index we have discussed. Now, let us look into the reasons why we get material dispersion. In order to understand material dispersion, we need to know what is the material that forms the optical fiber. And it turns out that glass is the material that is used. Glass is sometimes called as the host material because you will be doping this glass with certain other dopant materials in order to increase or decrease its refractive index. Glass or silicon dioxide SiO2 is the fundamental material or the major material that is used to make fibers, glass fibers or silica fibers, and this has a typical refractive index of about 1.44. Now we know that the core part of the glass has to have a higher refractive index compared to the cladding, and in order to increase this refractive index you have to dope this material with certain dopants, and these dopants can be increasing the refractive index, certain dopants actually decrease the refractive index. Okay. So if you look at the refractive index as a function of the dopant addition, so how much in percentage or in how much in mole you are actually adding this dopants and what happens to the overall refractive index, you see that glass has a certain base refractive index of say 1.44, and if you add certain materials such as boron or fluorine, these will actually reduce the refractive index. So this is basically for the fluorine and this is the boron dioxide or boron trioxide, I am not very sure, but this is boron atoms. Okay. So if you dope your silica with these atoms, fluorine or boron, you are going to reduce the refractive index. Okay. And the amount of reduction of the refractive index depends on how much the doping that you are going to add. Of course, when you add these dopants, you are actually creating certain mixture of the glass host and the dopant atoms, and the structural properties of the material will also change. By structural properties I mean the tensile stress, the strain and the bending effect, all those properties, the elastic properties, inelastic properties, the internal absorption properties, these are all actually changing. So you have to be careful in adding the required amount of the dosage or the dopant and not change the structural properties of the glass too much. Okay. If you want to increase the refractive index, well, you have to do something like adding germanium, which will increase the refractive index. So this is for increasing the refractive index. You can also add certain other materials in order to increase the refractive index. Now typical optical fibers that you find in market are made up of germanium silicon core, okay, so that the refractive index is actually higher here in the core region and it reduces slightly if you had silicon dioxide cladding at the outer end or silica at the cladding. Okay. You can of course also make another one, phosphorus I suppose, and then you can add or dope that one in the core, and then in the cladding you keep SiO2 itself. You can also make the core consisting of only SiO2, right, and then add a dopant in the cladding region, so that you might for example try SiO2 B2O3 addition. Okay. So you can have possible variations in order to come up with the refractive index profile that you want. These are what we have shown for the step index. If you want to obtain graded index, then you have to also add impurities as a function of radial distance, right. So that's a little more complicated than the refractive index profiles, but you can actually obtain refractive index of almost any shape, and you will see that most modern fibers have for different applications have very complicated refractive index profiles. Okay, and that is all coming basically by taking the glass host as the main material and then adding required amount of dopants at certain regions in order to change the refractive index. The local refractive index changes by the addition of dopants. Here is an exercise for you. I will consider one of a very interesting profile which is used to flatten the dispersion. Okay, we will talk about dispersion later, the dispersion coefficient, but this structure is used to flatten the dispersion, and this is called as a trench in the cladding, okay, or sometimes called as the depressed cladding structure. So you can imagine that this radius is A and let us say this one is some B, all distances are measured with respect to the center of the fiber, and let us say this edge is at a distance C. So you see that there are certain areas, right. So you have a core and then you have a clad and then there is also a trench in the cladding, right. So there is also a dip or the trench in the cladding. The exercise is that assuming that you have SiO2 material as the core, then can you come up with the required dopants depending on whatever doping you want. It's not that you have to give the exact percentage, but I just wanted to identify which dopants would be good in order to obtain the structure in the cladding in this fashion. Okay. Then you assume that I am not even specifying the core. Okay. This exercise is two part. One, you assume that the core is SiO2, then don't assume anything about the core. Then you come up with your own material, okay, in order to realize the refractive index profile that is shown here. Okay. Now what you can see is that you can add dopants to change the refractive index, but is this refractive index constant? Well, your earlier studies in optics would have kind of led you to think that refractive index is a quantity that is independent of frequency, because when we talk of geometrical optics problems, we say that a ray of light has been incident on glass at 30 degrees, right, and then there is a reflection, there is refraction, you calculate all those angles. Nowhere you kind of seem to talk about the frequency or the wavelength, but in fact it turns out that refractive index is the response of the materials. It is the response of the material to the external electric field and how the material rearranges itself, which is defined by what is called as a dielectric permittivity or the dielectric constant, although it is not constant because it depends on the frequency. So this dielectric permittivity is the root cause of the refractive index. In fact, refractive index is given by square root of the relative permittivity of a dielectric medium, okay, and this dielectric permittivity is a function of frequency. So clearly frequency or wavelength. So clearly this refractive index is also a function of wavelength, and that is what is going into the group index Ng. If you look at the group index term which we looked at in the last class, there is a term which says dn by d lambda. Dn by d lambda tells you how the refractive index n is varying with respect to lambda, and that term is the one which causes the group index and the group velocity. And you can imagine now that since dn by d lambda can exist, d square n by d lambda square can also exist. That is a second order derivative for the refractive index can exist, and you are right, and that would again cause the group delay dispersion. In fact, that is related closely to the group delay dispersion. Okay. So we have already seen, let us recap starting by Ng. We have already seen that Ng is given by n plus omega dn by d omega, indicating clearly that you have to consider the refractive index variation as a function of frequency. You can of course write this omega times dn by d omega in terms of the wavelength and write this as minus lambda 0 dn by d lambda 0, where lambda 0 is the free space carrier wavelength, right. So this is the expression you can substitute into Ng and then recognize that n can be written as a function of frequency or as a function of wavelength. You can write this as n of lambda minus lambda 0 dn by d lambda 0, rather n of lambda 0 again. So this will give you the group index. Okay. So this is the one that is actually giving you the group index, and the group velocity Vg will be given by C divided by Ng. Okay. And if this is the group velocity, if you consider a fiber of a certain length L, then if you consider sending a pulse of certain envelope here, then the envelope would arrive at a group delay of L by Vg. Okay. Group delay can be rewritten as L by C because Vg is C by Ng, and remember what is Ng? Ng is nothing but this fellow. So you can write this as n of lambda 0 minus lambda 0 dn by d lambda 0. So this is the group delay that you are looking at, and this group delay is dependent on the material. Now this is the group delay of a particular wavelength lambda 0. Now suppose instead of having one single wavelength, which would not be possible even if you consider an ideal laser, what you actually have is a spectrum around lambda 0. So most sources have a certain spectral width. Okay. So this spectral width or the bandwidth of the laser or the light source that you are considering can be denoted as delta lambda, and now you want to find out what is the overall delay for a case where the light source has a certain spectral width. Right. Now this lambda 0 travels at a certain group index. This part which is lambda 0 plus delta lambda by 2 will travel at its own group velocity. So, you will have ng lambda 0 plus delta lambda by 2. So, this would have a different value compared to the value for ng at lambda 0, and clearly even this lower edge would have a very different value of the group index ng. Okay. So, you can find out what would be the overall delay here by writing this one, or by looking at the overall delays, which we can call it as delta tau, and writing this as d tau g by d lambda, which would tell you how the group delay is varying with respect to lambda, and multiply this one by the spectral width delta lambda. Okay. So, you can calculate this one. So, what would be d tau g by d lambda? So, this fellow can be obtained by differentiating the expression L by C d n g by d lambda. I will leave this as a small exercise for you to calculate what is this d n g by d lambda, and then it turns out that if you calculate this and then put that value into this delta tau, you will see that delta tau is given by minus lambda 0 L by C d square n by d lambda square, okay, which has to be evaluated at lambda 0, then multiplied by the spectral width delta lambda, right. So, it is simply telling you the difference between the group index at the upper portion of the spectral width, that is the largest frequency component or the wavelength component, and the smallest wavelength component here. Okay, that is what determines the overall pulse width. So, that pulse width turns out to be delta tau, and clearly this delta tau by L will give you the pulse spread per unit length, and sometimes this is also divided by the spectral width delta lambda in order to obtain the pulse spread, which is measured in time, and delta lambda, which is measured in meters, okay, and length, which is also measured in meters. Okay. So, this quantity is what is called as the material dispersion coefficient dm, and this quantity dm is typically measured in units of picosecond per nanometer kilometer. Okay. So, it simply tells you that if you know what is dm at a particular wavelength lambda 0, and you also know what is the spectral width delta lambda around that carrier frequency lambda 0 or the carrier wavelength lambda 0, and then if you propagate a certain distance L through the fiber, then you can calculate what would be the overall pulse spreading. Okay. And that factor dm depends directly on this factor d square n by d lambda square, right. That is one of the major factors which give you the value of dm. Of course, this dm would be equal to 0, that is no pulse spreading, when d square n by d lambda square would actually be equal to 0. Okay. So, writing down what is dm, the material dispersion, you have to divide this delta tau by L and delta lambda, you get minus d lambda square 0 by C d square n by d lambda square evaluated at lambda 0. So, this expression for dm tells you how the pulse would actually change, what would be the delay of the pulse, or sorry, what would be the pulse spread in terms of picosecond per nanometer kilometer. For a pure silica fiber, you can actually show that by properly measuring this refractive index n is a decreasing function of lambda. Okay, for the region of interest that we are looking at, say around 1064 to 1600 nanometer, this n as for the pure silica fiber would actually be a decaying function, and attempts have been made to capture this capture this measured data using some empirical formulas. These are known as Selmayer's coefficients. Okay, that is, you expand this n of lambda in terms of certain coefficients a, b, c, d, e. I believe 5 coefficients are sufficient, and this would actually be some powers of lambda. Okay, these are all multiplying some powers of lambda. The exact way in which this formulas, the coefficients a, b, c, d, e come from are actually determined by the experimental values. There is hardly any kind of a good theory in order to find out the values of a, b, c, d and e. But once you know these coefficients for the given glass host that you are working with, then you can construct n of lambda as a function of lambda. Okay. This is a very good approximation to the measured refractive index profile. Once you have the refractive index profile n, which is actually decaying function, you can then take a look at what would be dn by d lambda. So, let us plot dn by d lambda, and it turns out that this would be all negative, okay. So a better way would have been to write this in under the axis. So this would actually be at 0, this is actually minus 0.02, this is minus 0.018 and so on, okay. So this is how this dn by d lambda would go, and it kind of makes sense because n is decaying with respect to lambda, therefore dn by d lambda should actually be negative. Now more importantly, because dn by d lambda is okay, but my dispersion coefficient dm is proportional to minus d square n by d lambda square, correct. So I want to know how the second derivative of n with respect to lambda looks like, and that will look very interesting. So it will actually look with a positive value until certain region, and then it goes to a negative value. And if you dope this one with different materials, then you can control or you can shift the positions of where the 0 occurs a little bit here, okay. This is for the different materials. You observe one thing over here, you have d square n by d lambda square or equivalently dm, because they are proportional to each other. There is, consider any one of those curves, so there is a certain critical lambda which you can call this as lambda zdw. At this lambda zdw, the material dispersion actually has gone to 0, correct, which means that there won't be any pulse spreading if you were to send only one wavelength signal at this Z0 dispersion wavelength. And if you were to send in a very narrow pulse, or you send in a pulse with a very narrow bandwidth, then around this 0 dispersion wavelength, then because this dispersion itself is very small around that region, there won't be significant material dispersion caused pulse broadening, okay. Of course that would not be possible in the practice, because you then will be working with only a very short region around that and then wasting much of the other regions. So you can't afford to really do that one. So you do send in signals at various wavelengths, not just at 0 dispersion wavelength, but it is good to know that this 0 dispersion wavelength is going to 0 at some particular wavelength, okay. And around that wavelength, the value here is kind of quite small, and the slope of that one is what is called as a third order slope, or slope of beta 2 is actually giving you the third order dispersion parameter beta 3, okay. And if you can also further evaluate, you will be able to find beta 4, beta 5 and so on. Now the other interesting part that you have to observe here is that in this region, that is below 0 dispersion wavelength, this d square n by d lambda square is actually a positive quantity, right. Because this is positive, dm actually is negative, right. So I should actually write this as not dm, but rather write this as minus dm, because dm is proportional to minus d square n by d lambda square. So while where d square n by d lambda square is positive, dm is negative, okay. And this is what is called as the normal dispersion regime. In the normal dispersion regime, the characteristic is that the longer wavelength actually arrives at a shorter time. So actually the longer the wavelength that is contained, the shorter will be the arrival times, okay. Shorter time of arrival. Now go to the other region where d square n by d lambda square is actually negative, right. While d square n by d lambda square is negative, the corresponding value for dm is greater than 0, that is to say dm is positive here. This region is called as anomalous dispersion, okay. And anomalous dispersion is very important for pulse compression, because in this region if you were to operate, the pulse actually does not expand but rather contracts, okay. Of course initially only, if you take the length of anomalous dispersion to be very large, then eventually, okay, because of the chirping, then you will start to see that the pulse actually becomes broadened, okay. But at least in the small section of the fiber, you can actually compress the pulses. In fact, this is quite widely used for pulse compression, and it is also the region where you can find soliton propagation in the fiber, okay. So this anomalous dispersion region is characterized by having a positive value of dm or negative value of d square n by d lambda square, okay. Here what you can see is that the longer the wavelength, the longer will be the arrival time. So longer wavelengths will arrive at a longer with a longer arrival time. So this is a characteristic of the anomalous dispersion in the materials. Now we will stop with material dispersion. We will look at another dispersion quantity called as the waveguide dispersion. Now waveguide dispersion arises, as I said in the previous module, because of the geometric effect of waveguiding. So your electromagnetic waves are not propagating in free space inside an optical fiber, they are actually being confined because of the boundaries that exist for the core and the cladding. They are actually propagating as confined modes inside the fiber. So as they propagate in the confined mode, remember you can have multi-mode fibers or single mode fibers, right. Consider first the single mode fibers, because multi-mode fibers are typically having larger amount of dispersion and their obtaining the characteristic of the dispersion is also slightly complicated. To obtain a qualitative understanding of dispersion, you imagine a single mode fiber. Now one of the critical parameters that tells you how much energy is contained inside the fiber is the V parameter. And remember how the V parameter changes with respect to the propagation constant. It is not a linear region, it is linear relationship, it is actually a curved relationship, correct. So this is how, if you remember, the normalized propagation constant versus the normalized frequency for the fundamental mode would go like this. So this is for the LP01 mode, right. So you see that there is this curvature for the propagation constant, and this curvature is the result of directly having a certain core radius, right, certain core cladding interface. So it is actually the geometry. Now if you turn around and then make a rectangular type of an optical fiber, then the B versus V curve, right, will not be like this, it will be different. Okay. If you take for example a free space, then B versus V would have been a straight line. If you take B versus V for a metallic waveguide, then it would be slightly different, it would look like this. Okay. So depending on what geometry and what parameters you are looking at, this particular curve B versus V would actually be changing. Now what does it mean? Look at this, we have this cutoff value for single moded, right. So it is around 2.405, and we have mentioned that if you want to have a tighter confinement of the energy inside the core, then the corresponding V number should be very close to 2.4, right. It has to be as large as possible. Of course it cannot be larger than 2.4, then the fiber would not be single mode, it would become multi-mode fiber. But larger V means a smaller lambda, also means tighter confinement. Now this might be okay as long as you had a single wavelength to consider, but you actually do not have a single wavelength, you actually have a spread of wavelengths to propagate, correct, because you are modulating something, and the shorter the pulse that you are modulating, the larger will be the spectral bandwidth, and larger bandwidth means that you have to consider all wavelengths over this region. It might so happen, and it will happen certainly, the larger the spectral bandwidth is, that the V number drops off significantly for a certain lower end portion of the spectrum, and V number might increase more than 2.4 for a certain spectrum. You might avoid this condition, you can avoid this condition of having larger values of 2.405 by actually moving the carrier frequency down in such a way that you do get a reasonable you do get a reasonable value for V at some lambda 0, but at the same time the spread is more important. You can move it closer to avoid the high or the higher end portion of the spectral width being greater than 2.405 by moving the lambda 0 closer to this one, but then you will see here that the corresponding lower end regions are actually having a smaller values of V number, okay, which means that these modes don't, or the mode associated with these frequency components actually will spend a lot of time in the cladding, or will have an appreciable quantity in the cladding, and we know that the cladding refractive index is actually smaller, which means that portion of the energy actually travels faster, while the central portion, which is smaller for smaller wavelengths, or rather for the larger wavelengths, will actually be traveling slower, because V is inversely proportional to lambda. So you see that there is a difference between cladding and the core velocities, and this difference depends on what wavelength you are considering, and that is why you get waveguide dispersion. And you can tailor this one by adjusting the core cladding refractive index distribution, also changing this core radius A. You can tailor that dispersion by changing the refractive index profile. Do not consider the single mode profile, consider making the core area very small, okay, or consider having multiple trenches in there. So you do all this design, okay, and in order to change the geometric dispersion effect, and that is what is called as the waveguide dispersion. It turns out that for standard single mode fibers, the waveguide dispersion dW is mostly negative, okay, and the total dispersion in the fiber comes because of the waveguide as well as the material dispersion, okay. And material dispersion, we know that would be initially positive up to certain frequency and then it becomes negative, correct. When dm is positive, this is called as a normal dispersion regime, and when dm is negative, it is called as the anomalous dispersion regime. Now the total dispersion would be a quantity that is positive. So this is how my dm should go, and then once you add dm as well as dw, your overall dispersion curve would be going around something like this, okay. My pictures are not really nice, but what has happened is that the zero dispersion wavelength has been slightly shifted from the material zero dispersion wavelength parameter. So it has been slightly shifted, and in fact you can shift this zero dispersion wavelength from the 1300 nanometer, which actually is the material dispersion for the pure silica fiber. You can shift this zero dispersion wavelength to 1550 nanometer, which is the window for optical, low loss optical window for the communication purposes, right, by appropriately tailoring the refractive index profile. For example, when you make the core area very small, right, then you will get a larger dW, which allows you to shift this zero dispersion wavelength. But the drawback of this profile would obviously be that there is only one zero dispersion wavelength. So you have to perform all your modulation only around that wavelength in order to take advantage of zero dispersion, which obviously cannot be done because you have a larger number of users, so you have to multiplex, you have many channels, and you cannot just transmit everything only at one channel. So in order to overcome that defect, you introduce this trench kind of a refractive index profile, okay. The trenches I have shown are the kind of practical trenches, but for analysis purposes you can assume them to be step trenches and step index profile, okay. So this would be the index profile for a dispersion flattened fiber. What is dispersion flattened fiber? Here your dispersion actually will be 0 over a certain bandwidth, okay. So this would be the dispersion curve. I am not showing anything to the scale, okay. You can look at the actual data sheet of the fibers in order to find out where this dispersion flattening is happening, what is the range over which it is happening, okay. But this is essentially the idea. So you can create dispersion flattened fibers, which are extremely important for communication purposes. Now one of the things that commonly comes up when we ask questions to students about what light sources are used for optical communication, most students, without asking further questions or without giving further thought, would answer LEDs. True, LEDs are cheap, they are economical, they are available at a very low cost at all places, and LEDs are easy to rig up a circuit. They are also easy to modulate, data is easy to modulate on a LED circuit, you do not have to worry about modulation, demodulation. The only drawback is that LEDs do not really work for long distance communication. They are perfectly fine if you want to work within say about 100, 200 meters, or maybe push it with great difficulty to about 1 kilometer, okay. But if you want to communicate over to your friend at the other part of the country, they are simply not suitable. So modern optical communication does not use LEDs for long haul communications, okay. For shorter and very short haul communications like this within the room lighting or wireless optical communication, these are all performed by LEDs because they are cheap and they can be used there, okay. But they are not used for long haul communications, and the reason is very simple. We will talk about that reason by looking at what would be the maximum data rate with which you can transmit, okay, which in turn is governed, as you know, by what is the delay that, or the group delay that these that we have to tolerate, right. The larger the group delay, or the larger the pulse spreading, the shorter will be the bit rate of transmission, right. So consider a typical LED, okay, which has a typical spread delta lambda of about 40 nanometers. You can actually find delta lambda of up to 100 nanometers in practice, but this is a very good quality grade LED which has a delta lambda of about 40 nanometers. Its spectral operation is around say 800 nanometer, which was what the original or the first transmission window of optical communication was. This was way back in 1970s, okay. So today of course we are in 2016 and we do not really use 800 nanometer for long distance communication. So lambda 0 is 800 nanometer, delta lambda is 40 nanometer, and someone has measured this quantity d square n by d lambda 0 square, and they have given us this value of 4 into 10 to the power 10 per meter square. I hope the units of per meter square is evident because n does not carry any units, lambda carries a units of meter. So this one is 1 by meter square. Now can you calculate what is dm? Also calculate what would be the pulse spread delta tau. So you have to calculate what is delta tau per L. Remember, delta tau is the pulse spreading. In order to get the pulse spreading, you do not really have to know the sign of this dm. So you can just look at the absolute value of dm, which will turn out to be lambda 0 square by c into d square n by d lambda 0 square. That delta lambda into L has been thrown away in this particular case because dm is actually a quantity which is per picosecond per nanometer and kilometer. Okay. So you first find out dm, you can substitute the values here. This is 800 nanometers or 8 micrometer, so you can put that one there. The velocity of light is 3 into 10 to the power 8 meter per second, and then d square n by d lambda square is given as 4 into 10 to the power 10 per meter square. So you plug in all these values, you will get the absolute value of dm as 107 into 10 to the power minus 6 seconds per meter square. Converting this into the units of picosecond per nanometer kilometer will give you 107 picosecond per nanometer kilometer. Okay. So this is the material dispersion for the LED that has been measured. Now this is by itself not very important. What is important is what is the product dm into delta lambda, and what is that product? This is roughly 40 into 100 picosecond per nanometer kilometer. So this is 40 nanometer, so nanometer goes away over here, you get around 4000 picoseconds per kilometer or 4 nanosecond per kilometer. Remember, we have talked about this B into L product, right? So B into L is the bandwidth into L product, and we have talked about that if you want to transmit at B, you are transmitting one pulse every 1 by B seconds. So you are transmitting this, and if you ask that no, this is the rate at which the pulses are coming out, or this is the time period of the pulses, and if you say I can tolerate about 0.5 times the pulse spreading, right? I can tolerate the intersymbol interference of about 5 times, I mean 0.5 times the pulse spreading, then 0.5 times dB should be equal to delta tau that we have calculated, right? Delta tau is the pulse spreading. It can be about 50% of the original pulse period, let us say like that. Okay. Then you can substitute for TB in B here, this becomes 0.5 by B, this is equal to delta tau. You can say B is equal to 0.5 by delta tau, put this relationship back into the expression, and then you get 0.5 by delta tau into L. This would be the bandwidth into time product, and we have seen that this delta tau is around 4 nanoseconds per kilometer. Okay. So here you have delta tau as 4 nanosecond per kilometer. You can substitute this and then say if I want to obtain data rate of 10 megabits per second, what should be the value of L. So I will just leave it for you guys to calculate this one. This would be a small exercise to you. So with dm turning out to be this value, and if you want a data rate of 10 Mbps, find out what is this length over which you can propagate. Okay. So this is for the LED. Now consider a laser. Okay. A typical laser has a line width of 0.2 nanometer. Okay. This is of course not the best of a laser. The best kind of a lasers today have about 100 to 200 kilohertz of line width. These are extremely small line widths that you actually get, but this delta lambda will be around 0.2 nanometer, is a typical about 10-20 years ago what would be the laser. Okay. So let us take that value there, and the value of d square n by d lambda square is slightly less for this laser. It is 1 order of magnitude less, and this is given by 2.7 into 10 to the power 9 per meter square. You can substitute for dm and calculate that this will turn out to be 13.5 picosecond per nanometer kilometer. If you compare this value, it is not very large, I mean it is not very drastically different, it is just 1 order of magnitude lesser than dm for the LED. For the LED you had 107 picosecond per nanometer kilometer or about 100. Here you have 13.5 picosecond, which can be thought of as 10. So there is just one order of magnitude reduction in dm. But this is not what gives us the advantage of a laser. The advantage comes here because of this 0.2 nanometer decrease in the line width. Why? Because you calculate delta tau turns out to be 13.5 into 0.2, right, so many picoseconds per kilometer. This is actually around 2.6 picosecond per kilometer, which is 1,000 times less than what you had for the LED case. You know, it is an order of 3 magnitude less compared to the case of a LED. Therefore, the data rates can be tripled at the very least. At the very least, you can triple the data rates using a laser. So, you can propagate much larger distances, you can propagate with a larger bit rate using a laser. Therefore, the reason why we use lasers for long haul communications or any communication that has to take place for more than a kilometer or about 10 kilometers is because you can transmit at larger data rates using lasers. Lasers have a smaller delta lambda, smaller spectral width. Okay. So, next time when someone asks you what kind of a light source is used for optical communication, I do hope that you are going to ask the questioner back saying that are you talking about very short haul or indoor wireless kind of a transmission system or a long haul system. If it is long haul, then it has to be a laser. Okay. So, lasers are the reason why you can have this long haul communication. The final dispersion that we wanted to talk about is what is called as polarization mode dispersion. Now, this polarization mode dispersion is kind of very difficult to model analytically. Okay. It was initially discovered in the decades of 90s, where people started going from 2.5 Gbps systems to 10 Gbps systems. So, when that upgrade happened, then they figured out that PMD was one of the main limiting factor for for not being able to go from 2.5 to 10 Gbps systems, and lot of studies were done, but still a thorough theoretical reason as to why PMD arises is not possible to has not been found, but excellent studies have shown that the spread because of the PMD, right, is directly proportional to the square root of the length of the fiber. Okay. This square root of length can be thought of as some kind of a random walk. A typical random walk is one where you take with a certain probability one step towards the right and a certain step to the left with a certain probability. Okay, one step to the left with a certain probability, and if you wait for large number of steps, you would see that you are actually not just sitting at the initial point as you would expect intuitively, but you would actually be arriving at a point which is square root of n. So, that is the average position after taking a large number of steps, sometimes to the right, sometimes to the left. So, in that context, which is called as the random walk problem, so you can think of this PMD as power exchange or the mode exchange between x to y and y to x with a certain probability and over a certain length. We will later give you MATLAB exercise to realize all these things. There is a nice way of formulating this problem, okay, using simple matrix approach called as Jones matrix approach. You will be solving that, and you can see what will happen when the polarization mode dispersion actually occurs, and then the pulse basically spreads out. Okay. So, we have looked at these different dispersion characteristics. It is time to wrap up this dispersion and then go to another factor which is called as attenuation. Okay. Attenuation, again, the mechanisms whereby attenuation occurs in fiber can be intrinsic, okay, and this intrinsic includes absorption, it can be scattering of light, and it can be extrinsic. Extrinsic factors such as bending, stress, etc. can cause attenuation. We will not consider this attenuation now, and we will of course not even be considering the full picture of why attenuation occurs. This is something that is left best for material science people to explain better. But if you look at the attenuation versus wavelength curve for a silica fiber, you will see that attenuation is very large at X-ray wavelengths, at very short wavelengths less than 400 lambda, 400 nanometer, the attenuation is very large, okay, and this happens because of the electronic transitions. At very small wavelengths, the energy of the photons are quite high, because energy is inversely proportional to lambda. It causes the materials in the lower state to go to the upper state, okay, thereby inducing a transition. So, these electronic transitions cause attenuation of the signal. You will see that at longer wavelengths there is an intrinsic absorption, that is at the IR region there is an intrinsic absorption here, this is the UV region. So, this absorption keeps on increasing beyond around 2 to 2.2 micron for a silica fiber. In between this is what is called as a low loss window, which you will find some amount of vibrations, okay. These are because of some metals which are present in the fiber, and then you will also see some water peaks which happens because of the impurities in the form of the hydroxyl ions, which are used actually to when they are actually being used to fabricate, when the fibers are being fabricated, then connecting this would be the low loss window, okay. In fact, modern methods actually have almost eliminated this peaks, hydroxyl peaks or the impurity ions, water impurities, and thereby lowering the losses. So, this region, you know, is called as the optical region, right, and in this region is where your communication windows are located. Earlier this was located at 850 nanometer, then it became 1300 nanometer, and today you are on this 1500 nanometer window or 1550 nanometer window, where the losses are at its lowest. Over about 100 nanometer the losses are pretty small, they range from 0.15 to 0.25 dB per kilometer. Now, what exactly is this attenuation loss? What it simply means is that if I take a fiber of certain length L, okay, and then send in a certain power, which let us call it as P of 0 at Z equal to 0, and then measure the power at the end of the fiber, which we will call as P of L. It can be shown that this P of L, okay, can be given as P of 0 into e to the power minus alpha into L, where L is the length of the propagation. So, this kind of a exponential relationship is empirical, of course, this is phenomenological relationship, it does not come really from the fundamental physics or something, but this is an excellent approximation for characterizing any loss in the fiber, okay, and losses are characterized by changing this value of alpha. You can find out what is alpha. Alpha is simply given by P of L divided by P of 0, you take the natural log on both sides and divide this one by L, okay. So, if you do this one, then you will get the attenuation, right. This attenuation is measured in Nepper per meter or simply per meter, but it is more common to actually specify attenuation in dB per kilometer, okay. So, the relationship between alpha in dB per kilometer to alpha in Nepper per meter is this one. So, it is around 4.343 times alpha in Nepper per meter, okay, Nepper per kilometer, I am sorry, okay. Why this dB per kilometer thing is important? Let us consider a simple example. In the 1970s you had losses of 20 dB per kilometer, okay. So, this was a typical fiber in the early 1970s where the losses were 20 dB per kilometer. Suppose I send in 10 milliwatt of power, okay. What would be the power that you expect at the output of say 1 kilometer? Since the loss is 20 dB per kilometer and input is 10 milliwatt, you can either express this 20 dB per kilometer into Nepper per meter quantities or express this power into decibel quantities and then subtract them, and then you can get the corresponding expression. This is what we normally do. We consider how much power you are in. Suppose P is the power in milliwatt, divide that one by 1 milliwatt, take the log to the base 10, multiply by 10, and what you will be defining is a quantity called power in dBm. It is simply telling you how many decibels above milliwatt my particular power P is, okay. For 10 milliwatt this corresponds to 10 dBm, okay. So, it is 10 dB above 1 milliwatt, okay. Now, this power is launched, and to obtain the loss at this point, because you are working in the dB scales, all you have to do is subtract this alpha into L. When alpha is expressed in dB per kilometer times the length of the propagation will give you the total loss. This loss will be in dB, right. So, this was at this level, okay. This power was at compared to 10 milliwatt. So, if this is my base 1 milliwatt, 10 milliwatt means 10 decibels above 1 milliwatt, right. And then losses would mean after subtracting the total losses, you have to be at a certain above or below depending on how much loss you have. In this case the total loss will be 20 dB. So you started off with 10 dBm, then after losses you have gone down to 10 minus 20, which is minus 10 dBm, which is 0.1 milliwatt. Okay. So that is the kind of power you are looking at for a 1 kilometer transmission. This is the power that you are looking at. Okay. If I turn around the problem and then tell you I don't know what is the length of the fiber that I want to use. I know the attenuation is 20 dB per kilometer. However, I am able to detect any power which is at least minus 20 dBm. Can you find out what would be the length L? Well, assume that the initial input is 0 dBm. 0 dBm corresponds to 1 milliwatt. Okay. So you learn how to do all this conversion using those formulas which I have given you. So 0 dBm corresponds to 1 milliwatt, and I can actually measure up to minus 20 dBm using my photodetector circuit. What would be the maximum length of propagation that I can choose? Well, the total loss is 20 dB per kilometer, right. And if I consider 0 dBm and add this loss which is minus 20 dB, what I get is minus 20 dBm, which is just sufficient to measure the power. So if I take 1 kilometer, the total loss is 20 dB and I am actually able to transmit over 1 kilometer. That is the maximum distance over which I can transmit. If I increase from 0 dBm to 10 dBm, then the length also can be increased, because I am looking at a total loss of 10. So I have to start at 10 dBm. To get down to minus 20 dBm, I should have a loss of 30 dB, right. So 10 minus of minus 20 is the total loss, which is 30 dB loss, but this loss divided by alpha will give you L, because alpha into L is so and so dB loss, correct, and alpha is measured in dB per kilometer. So if you do that one, you will get 30 by 20, which is around 1.5 kilometer. So if you start with 10 milliwatt power, right, and then you will still be able to go only up to 1.5 kilometer. Consider this scenario and compare it with optical fibers whose losses are around 0.2 dB per kilometer. Again, the same minus 20 dBm is my sensitivity limit or the minimum power that is required for the receiver. I start with 0 dBm or 1 milliwatt optical power. Then what would be the length over which I can propagate? Well, the losses total will be 20 dB. So 20 divided by 0.2, which is about 100 kilometer, correct. So this is the length over which I can propagate. If I increase from 0 dBm to 10 dBm, then the distance over which I can propagate will be 30 by 0.2, which I suppose will be around 150 kilometers, right. So you can see the tremendous improvement from the earlier optical fibers, which you could go only up to 1 to 1.5 kilometer. Compare that same fibers today with losses as low as 0.2 dB per kilometer, the transmission distances have increased to 100 and 150 kilometer. In fact, this transmission distance of 100 kilometer, roughly 100 kilometer is the span length. So before which you will have to put in your repeaters in the optical communication system. So for a long haul communication system, this 100 kilometer is the span length. So this completes our parameters of the fiber. To just briefly recap, fibers are made of glass materials. This glass material doped with appropriate dopants in order to increase or decrease refractive indices. These dopants and the glass material itself is a function of the refractive index is a function of wavelength, and d square n by d lambda square, which tells you how the refractive index is varying, the second order refractive derivative of n with respect to lambda will give rise to material dispersion, okay, which simply means that the pulses are going to be spread. An additional dispersion is the waveguide dispersion, which occurs because of the geometrical aspects of the fiber, and a third dispersion is the polarization mode dispersion, which happens because of the random exchange of the power or field between the two modes of the single mode fiber. Okay. The overall dispersion is determined by all these three quantities in a single mode fiber. For a multi-mode fiber, you also have to consider intermodal delay, that is delay between HE11 mode and TE12 mode, for example, right, the first and the next higher order mode or between the higher order modes. So multi-mode fibers are typically much more prone to dispersion than single mode fibers. Finally, attenuation is a mechanism which reduces the optical power. So, this if you start with say 1 milliwatt at the input of the fiber, what you get after 1 or 2 kilometers of the fiber will not be 1 milliwatt. There will be reduction in the power, and how much power is reduced is determined by the attenuation coefficient of the fiber. So, this completes our parameters of the single mode fiber. In the next module, we will go back to communication concepts and study the simple modules in order to put them together, and we will then look at optical sources and optical detectors later on. Thank you very much.